So good evening. Last class when we were introducing the idea of analysis of variance, if you recall, we talked about the fact that ANOVA primarily came into existence as a statistical tool when we started looking at comparing more than two columns of variables. Okay, so with two columns, it is always a t-test that will um, solve the purpose. When it comes to more than two columns of information, you can still do t-tests, but taking two at a time. But that's where the ANOVA is a one-stop shop as a single test. And we introduced some of the terminology that goes typically into design of experiments in ANOVA, like a factor. It is nothing different from an independent variable of interest, or the X variable, as we know. Um, we also talked about um, the factor level. So we were uh, discussing a package design in the context of things last time, and there were four levels of the package design, and each level is also called a treatment. Okay, the same can be thought of as we will discuss the house pricing data set that we discussed at the beginning of this class. And in that context, a neighborhood can be one of any three: neighborhood one, two, or three. And so each one of them would be a level for the neighborhood, which is the factor, and each one of those neighborhoods would be a treatment. Okay, so experimental design essentially encompasses the determination of the number of factors, number of levels in each factor, and the dependent or the response variable. So number of factors is how many x's, number of levels of each factor. So if x is a factor, x can have multiple levels. Okay, so if this is sex, that can be male and female. Okay, if this is um, uh, level of education, that can be um, freshman, sophomore, junior, senior. Those can be all levels within that factor. Okay, if this is neighborhood, like in the example we talked about at the beginning of this semester and that we will discuss tonight, it can be neighborhoods 1, 2, and 3. Those are all levels. And then you have the dependent or the response variable, which is your y. So this goes back to the discussion we had at the beginning of our semester, where we talked about y being a function of x, and you are trying to essentially model that relationship. And so in this case, with a single factor, you're modeling that. Okay, so the example that was discussed briefly in last class was one of a cereal company that was interested in testing 4 new designs of their product. 10 stores were randomly chosen, and the sales um, and the number of cases of cereals that were sold were recorded. So each one of these are the records of the cases of cereal. As you can see, the the J factor, or the column subset, corresponds to the specific design of the package. Okay, the row value basically is one of those 10 stores that was randomly assigned to draw that data. Okay, so in essence, your factor is your package design. There are 4 different package designs, so 4 levels or treatments. You are trying to see if package design impacts sales. In other words, you are trying to model sales as a function. That F stands for a function. You want to model sales as a function of package design. And then there is some random error that you are not taking into consideration. And we talked about this in the last class. That's how we ended. We said, um, can there be other factors that are affecting sales other than package design? And the answer is an absolute yes, right? So taking all of those factors into consideration, it would be a more wholesome, a more holistic model. This model specifically looks into package design as the only factor and trying to understand how that factor impacts sales. And therefore, for everything else that has not been considered, you are looking into something that we define as your random error. Because we have only one factor that we are using in this model, and that factor is package design. It is also called a one factor or a one-way design of experiment, or a one-way ANOVA design. So here is a more specific example around that same concept with real numbers. So as an example, the Fagan Food Company wants to test 4 different package designs for a new breakfast cereal. 13 stores were selected as test sites. Sales in the number of cases of cereal sold after 3 weeks are shown as below. So you have um, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. In total, you have data on sales from 13 stores or 13 test sites. Okay. And they have been categorized by the typical package design that was used in each of those stores. Okay, so if you look back at the previous page, it's the same setup, only this time we have provided numbers to it. Okay, so from the first test site or the first store, um, 10 of those cereals from package design 1 were sold. Okay, um, from the next test site, 11, from the third one, 12, and these were all from package design 1. In the same way, these all came from package design 2, this one from package design 3, these came from package design 4. So what you see here is the total of each of those package designs. This is the grand total. The average numbers sold for each of those package designs, and this is average specific to package design 1. On an average, package design 1 sold 11, package design 2 sold 14, package design 3 sold 19.5, package design 4 sold 27. And so this is the grand average of 17 from all of those stores, 13 stores taken together. And of course, of those 13 stores, the division was 3, 4, 4, and 2. So the question that we are trying to answer is, statistically, is there a significant difference in average sales for the 4 package designs? Okay, so if you want to define that as an equation, your response is your sales, your factor is your package design, which has 4 different levels or treatments: package design 1, 2, 3, and 4. And therefore you are defining sales as a function, and this is where the term F comes in. You're defining sales as a function of package design, and then you are saying that everything else that impacts sales that has not been considered in this model is a random error. Together, they complete the definition of what impacts sales. What I'm capturing number wise, numerically, is only what is happening from package design. There can be multitude of other factors that are also impacting sales. I'm only looking at the package design piece of the puzzle. So, is there a significant difference in average sales for the 4 package designs? And this was a discussion that we were having in the last class. If you just look at these numbers, right? These are the average sales numbers by the package design. 11 from package design 1, 14, 19.5, 27. So just on face value, can you conclude that package design impacts sales? Just on face value. Yes, no?
Dr. B, I have a question.
Yep.
Are we assuming that each row is a store?
No, each row is where the package design 1 has been implemented, 2 has been implemented, 3 and 4. Each one of these is a store.
Is it consecutive to each package design? So for example, store 1 had X amounts of package design 1, 2, 3. So it's all the same store going in one row?
No. This is where you don't know that data as to which store it's coming from. That doesn't matter.
Okay.
It is one of those 13 stores. These are 13 randomly chosen stores. All you know is for these 3 stores, they are coming from package design 1. For the next 4 stores here, they're coming from package design 2, and so on and so forth. Okay, so if you recall in the previous page, that is exactly what I mentioned. I said the row value doesn't really mean anything statistical. The row value here was, I was just giving an example of probably which store it was coming from, but it doesn't mean anything statistical because it could have come from any of the 10 stores, right? The same way in this example, I have 13 stores that were selected. It doesn't matter where it's coming from. All it matters is which package design is being used. Okay. So I go back to my question. Is there a significant difference in average sales for the four package designs? Without doing any statistics, just by looking at these numbers that I am highlighting here, can I have a feel? Can I sense something? Whether package design impacts sales or not?
It looks like number 4 is a lot.
Absolutely. It looks like number four is a lot higher than the other two. Thanks, Amy. And yes, um, there is a feel that package design seems to impact sales, but you can't infer. You can't infer, and this goes back to our learning of sampling techniques, right? You can't infer because this is just coming from these 13 stores. If I go back to the bigger population of stores and randomly choose another 13 stores, those numbers can be different. So therefore, when I have to infer, this is where the statistical significance has to be taken into consideration. That's where your confidence, your alpha, 5% chance of rejection, and all that jazz comes together. So very broadly, if you look into the analysis of variance based off of these four different columns of data, each column representing a treatment or a package design, very broadly, your hypothesis is the status quo being the average sales are equal across all four package designs. You're saying that if the average sales are the same across all four package designs, then there is no change in sales due to package design, or in other words, package design does not impact sales. That becomes then your null hypothesis. Mu1 equals mu2 equals mu3 equals mu4 equals mu. They are the same. The alternative hypothesis is that any two are different than the others, where at least two means are not equal to the rest. As long as we can prove that, we can also make the case that at least one of them is different from the other, and therefore package design does impact sales. So that becomes then the alternative hypothesis.
Dr. B, can I ask a question?
Yep, please.
Why is it that at least your alternate hypothesis is that at least two packages designs are different? Why couldn't it just be one?
At least two are different from each other. That's what I meant.
Oh, thank you.
Yes. So when you look into, and let's now look into the statistics of things, and I want to explain this in the context of the problem. Don't get blown away by these expressions. I'll make sure that these expressions mean something to you. Okay, so when you talk about sum of squares of deviations, you are trying to see how much of a difference, how much of deviation does each point have from the broader mean. Okay, so y sub ij is any one of those 13 store figures. Think about it that way. Okay, so y sub ij is any one of those subsets, any one of these 13 points, let's say. And what you see as y bar here, this is the cumulative average. In other words, it is this guy 17 here, y bar. This is the overall gross average from all of those 13 stores. Okay, so when you are trying to capture variability, in essence, you are trying to see how far different is it from the average. If you recall our discussions from, I don't even remember, learning module 2 or 3, when we started talking about how to capture variability. If you recall that discussion, we talked about how much away is each point from the expected value or the mean, right? That's where the discussion started, the deviations. And then of course we squared that deviation and take the square root to find standard deviation and all that jazz, right? But the starting point always is how much deviation is each data point from the overall mean. Okay, so that is essentially what y sub ij minus y bar means. Okay, so that is the deviation you are trying to find for each of those data points or any one of those data points from the gross mean or the overall mean. And then of course, when you square that term, then it becomes the sum of the squares. If you sum them up and you square that term, that's essentially what you are looking at in terms of this expression. Okay, so all you are doing is you're looking for each specific term, which is the sales values for each of those 13 stores. You are seeing how much deviated it is from the overall mean. You are looking at that square of the deviation and you are summing that all up. And so that is the overall variability that is there in that data set. Now the fun factor here is how can we decompose these into two parts and actually make it meaningful for each of these parts. And so mathematically, this concept is very easy, but I don't want you guys to look at it only from a mathematical standpoint. Once we understand the mathematical standpoint, I want you guys to also understand what each of those components mean. Okay, so let's look at the mathematical piece first. Okay, so and then this is a very simple high school kind of a problem. X minus y. Okay, if this is an expression x minus y, can I also rewrite this as x minus 4 plus 4 minus y? Yes, no. Yes,
Yes.
because your negative and positive 4 crosses out, and so essentially this is the same as x minus y, right? Yes, no? So in other words, I can write this expression x minus y as x minus 4 plus 4 minus y, and now suddenly I can rewrite this again as two buckets. One is x minus 4, one is 4 minus y, and they still mean the same thing as this original expression. Everybody with me? Yes, no? This is a very simple take on the subject mathematically. All I've introduced is just a constant. I put a negative value of the constant. I put a positive value of the constant because they cancel each other and the remaining part remains the same. And so I am rewriting that expression x minus y as x minus 4 plus 4 minus y. Everybody with me? Yes, no?
Yes.
Fantastic. So that same concept works here. As you can see, y sub ij minus y bar is being written as y sub ij minus y sub j bar plus y sub j bar minus y bar. So this is a negative value, this is a positive value. They basically cancel each other out. In the same way 4 cancels, negative 4 and positive 4 cancel each other out. And now I can really use the parenthesis to create two distinct buckets. And if you're asking yourself the question, what do these buckets mean? Let's look into what y bar means first. Y bar is the overall mean of all of those data points, right? So that 17 here is your overall mean, which is y bar. Each data point here of these 13 pieces, each one of them is your y sub ij, right? Which are the specific data points. And then you have the averages for each of the package design. The average for package design 1 is 11. That is your y sub j bar, where j bar equals 1, where j equals 1. This is y sub j bar, where j equals 2. That is 14. 14 being the average of the package design 2. 19.5 being the average of the package design 3. 27 being the average of the package design 4. So 11, 14, 19.5, 27, all of those, each one of them are that y sub j bar, which basically means the specific sample mean for each of those package designs, where j is the package design, j being 1, 2, 3, or 4. So now suddenly those buckets have a very specific meaning, because now when I say yi sub j minus yj bar, it's basically telling you within a certain treatment, because this is all within that treatment of y bar j. Within a certain treatment, what are the deviations? So in other words, it's the difference within a treatment. In other words, you are trying to see how much different they are between these numbers, how much different they are between these numbers, how much different they are between these numbers, between these numbers. Okay, so that is within the treatment. Okay, each of those numbers, as the rows, as the columns that you see, represent a specific treatment. So within that treatment, how different are they? That deviation is captured by y sub ij minus yj bar, where yj bar represents the average of each of those treatments. And so how far different are each of those data points from its respective average? That is what that difference is managing. It's also called the difference within the treatment. And then if you look at the second bucket, it says y sub j bar minus y bar. In other words, you are trying to manage the difference between a specific treatment average and the overall average. And you are trying to see if that difference is real. So this is where you are really seeing whether between treatments there is a difference or not. So that's where you are comparing the specific treatment average and you are comparing the overall average. And you are trying to see if there is that difference realistically, statistically or not. So that is what is represented here in this equation. The y sub ij minus y bar is your total difference. Okay, so for each data point, deviation from the total mean, that's your total difference. And if you break it up by using a very simple mathematical expression of plus minus the same value, in this case, you're using the treatment mean as that value, you actually can create two separate buckets. The first bucket being how much of a difference is there within the treatment and how much of a difference is there between the treatments. Okay, and so that total in a simple form is represented as a within, that is error, and a between, that is real, between the treatments. So my question to you before even we go any further, the underlying question that we are trying to answer is whether package design impacts sales or not. To make a case that package design impacts sales, if this is A and this is B, which one of these differences you want to be larger than the other? That will help you make the case that package design will actually impact sales.
Would you want the differences between treatments to
Between
be larger
treatments
than
or
within?
B, you want that to be high, right? Because once that is high, you know that you have a good working model to deal with. That is something using your experiments you can control. Do you have any control on this aspect, the within part? Not too much. It is what it is. And you want that to be low. You don't want that to be too high. Because then if the within part is too high, what happens is it's basically telling you there's so much more than package design that's impacting your sales. Package design is a very small piece of that puzzle. But as Ms. Shikora said, when you are talking about the between treatments, you are trying to find that value and you are expecting that that difference is significantly high or considerable enough that you can make a case that package design impacts sales. So when you sum those up and you square those terms, this is what you get. The SST stands for the sum of squares total. The SSW or SSE oftentimes as it is called the sum of squares of the error. And this is the sum of squares of the treatment or between. But at the same time, you are also looking into degrees of freedom that are offered to each one of these. So overall, you have 13 scenarios. So you have 12 degrees of freedom, but you can use the same concept. In this case, C represents the number of treatments or the number of columns. Okay, so C is 4. So your N is 13 and your C is 4. C corresponds to the number of treatments. And so your degrees of freedom, total degrees of freedom is N minus 1 or 12, but that can be represented as N minus C plus C minus 1 for the within and the between respectively. So when you are talking about between treatments, if there are 4 treatments or C equals 4, the degrees of freedom are 3. And then the remaining ones, the remaining 9 is your N minus C, which is the degree of freedom for your errors. Okay, so that just becomes a given. So these already we know from our concept of how we design the t-test and stuff. If your N is 13, then the degrees of freedom turns out to be N minus 112. Your C is 4. We have 4 package designs. And so your degrees of freedom turn out to be 4 minus 1 or 3. So what an ANOVA table does, and this is why we are studying this, because the ANOVA table will come back to haunt us while we look into regression. It puts all of these things together, these concepts together. So you have the source of variability, okay? And in essence, there are 2 sources. One is between treatments, one is within treatments. And as Sarah mentioned, we are more concerned about the between treatments part because that helps us go back to our hypothesis and reject the null hypothesis. If the package design impacts sales, then you would want that variability, most of that variability, to happen from between treatments. You want the variability within the treatment or the error to be minimum. You want this guy to be high. Because then your sum of squares, sum of square of errors, that's how we captured them in the previous page. Then you have your degrees of freedom that you have for each one of those sources of variability. And if you take the first value and you divide by the second, you get what we call the mean square values. Okay, the sum of squares divided by the degrees of freedom gives you the mean square value. Sum of square errors divided by degrees of freedom gives you mean square value. And then eventually you get an F value or an F test. F stands for Fisher. Wrong spelling. I'm so used to a fantastic mathematics teacher in the Vigo County called Mr. Fisher. Fisher, Fisher. And that F test is essentially the MSB over MSE. That ratio is your F test. And then the decision rule is the same that we have learned. If that thing is more than the F critical, in this case, we just go by the P value. We have a corresponding P value that we also compute. And we go by the P value. If your P value is less than alpha, you reject the null hypothesis. And then you can conclude that the package design does impact sales. So statistically, you can say that at least 2 of those means are different from the others. But then from a human standpoint, you can conclude that um, package design impacts sales. And don't take me otherwise, statisticians are also humans. We are just different. Okay. So the reason I talked about this in length, looking into the, the preparation of the process, is it hopefully now would help you understand that table better as to where those numbers come from, what is the source of that variability, and so on and so forth. So if you look at the Excel spreadsheet that I asked you to open, the pdesign underscore ANOVA, okay, the Excel spreadsheet has two tabs, as you will see. Okay, the one tab that says for other software, and again, this is where Excel is a different kind of an animal. Excel is not designed to actually do statistical analysis. That's why we have add-ins that help us get through. Um, so for Excel, you now have to um, tame that data and build it in the same way that we just studied, so that Excel can break it into um, all of those four sales areas based off of package design. And only then can you actually do the Excel side of the story when it comes to the analysis of variance. For any other software, like in R, it is a very straightforward process. Okay. So we'll look into both of those, and we'll look into the output to understand what we have just studied. So let's look into the Excel side first, and we'll move into R very soon. Okay. So this is your data in the same way it was designed on the workbook, because that's how Excel reads through it. You have to differentiate each one of those four sales figures. The original data may actually come something as simple as this. So package design 1 corresponds to sales data, 2 corresponds to sales data, and this doesn't have to be sorted or anything. A good software like R will just pick it up just like that. Okay, with Excel, you have to train that data in a way that Excel can read it for its analysis of variance. Okay, so once you have that data set up in that order, what you would want to do is go under data, go under data analysis, and you see there are multiple options of ANOVA. We'll choose the single factor ANOVA because we are only looking into a single factor. The factor is package design. There are 4 levels to that same single factor. Okay, so we hit OK. We are looking at the input range. So we choose that entire input range, including the labels. It's grouped by columns. Labels in the first row. I'm going to use an alpha of 0.05. I'm going to use my output range right here. Let's say G2 in my case. And I hit OK. And what Excel does is creates a couple of things for me. One is it provides an overall summary data for each of those package design sales. So as you can see, there were 3 stores with package design 1 sales. Their sum, their average, their variance. So these are exactly the same numbers that we saw in the workbook. Okay. And then it provides an analysis of variance in terms of between and within groups. Okay. So what we want to take away from this, and let's build this in step by step, now that we have understood what this ANOVA table means. If I ask you the question, is there variability in the data? First question, simple one. Is there variability in this data set? Yes, no.
Yes.
Yes, there is absolute variability in the data set. Is there a specific number in the table that tells you what that variability value is? Think simple, think start beginnings.
Would it be the variance?
And what would that number be on this table? I'm just looking into this table, Ashley, the ANOVA table. So on this table, is there a number that can provide me an objective understanding of variability in the data set?
Would it be the 404?
Thank you so much. Yes, that 404 basically represents the overall variability in the data set. Everybody else understands that? Yes, no?
No.
So if you go back to the previous discussion that we were having, your total variability is what we covered, right? That total variability is essentially your sum of squares of total. That is how much deviated each point is from the overall average, right? That's the overall total deviation, and you take the square of the deviation. That is your measure of variability. So on an overall basis, if you look at a table like ANOVA, that total variability can be again divided into variability between treatments and variability within treatments, as we discussed. So if you just take that picture and superimpose that on the ANOVA output that we got from this specific example, this value of total, that is your total variability of sum of squares. SS stands for sum of squares. So sum of squares total, SST, the total variability is 404. It's a measure of how much variability is there in the overall data, taking everything into consideration. Okay. Now, there are two parts to it. One says between groups, and in this case, the groups are essentially your package designs, right? So you can basically rename this as between package designs and within package designs. So let's go back to the discussion that we were having. In order to make a case that package design impacts sales, you would want the variability between package designs higher or the variability within package designs higher. This is something we just discussed a few minutes back.
Between package designs higher.
You want the variability between package designs higher. And so if I ask you the same question that I asked a few minutes back, if the total variability in the data set objectively is represented as 404, how much of that variability is due to the package design itself? Can you give me a number from this table? If the total variability in the data set is represented as a number, let's say that number is 404, how much of that variability is due to package design?
$369.
369 is the right answer. So 369 is the part of the variability, total variability 404, that is between package designs, and therefore that variability comes from package design directly. And so right away, without looking into any statistics, you know that your numbers are favorable enough that your package design will be impacting sales. How many total data points were there? Total count, how much?
13.
13. Therefore, total degrees of freedom is
12.
12, right? Which is what you see there as the degrees of freedom, or DF. Total degrees of freedom is 12. How many package designs are there?
4.
And therefore, the corresponding degrees of freedom, which
3.
is C minus 1, equals 3. And then the remaining is, of course, your degrees of freedom for the within part or the error part, that's 9. The mean square, as I said, is that SS divided by 3. And if you take the ratio of the mean square from between package design to within package design, that ratio gives you the F value. So if I had to explain this to a layman, what does that F value mean? One way of saying that is variability between package design is 31 times more explainable than variability within package design. So it's essentially a ratio, right? Because it's measuring that 123 divided by 3.88, right? So it's measuring that ratio. It's telling you how much more explainable that package design variability is. And so that is a measure of your F test or your F value. Can somebody tell me if this value is high or low? 4.13 e raised to negative 0.05.
It's real low.
So it basically means 4.13 times 10 raised to negative 5, which basically means 4.13 divided by 100,000, which basically means that value is 0.0000413. That's a very, very low value in terms of p-value. And I can actually redo that here by looking at my home tab and just convert this from a custom to a number and make it 4 decimal places like I have talked about in the last class when you talk about probability. And that just becomes a very, very small value. It's just taking the first 4 decimal place and truncating it there. And therefore you see that p-value of 0.0000. Still with me? So now, something that we have all done quite a bit. Is p-value less than alpha?
Yes.
Yes.
Your alpha is 0.05, right? And therefore you can conclude that. What can you conclude?
Can reject the null hypothesis that they're
And you
all
conclude
treatments
that,
are equal.
yeah, the means are equal is a statistical approach to conclusion. I want a more non-statistical approach to conclusion in the context of the problem. So Lauren, restate that in a non-statistical form.
That essentially the package design does make a difference.
It does make a difference. Package design impacts sales.
Yeah.
That is what you're concluding. Exactly. So once you're able to conclude something like this, then you can look into which one of those package designs actually make a difference. There are multiple tests out there. I don't want to go that track yet because I want to build on this knowledge base and move into regression directly for this class. But do understand that there are tests like Tukey and Bonferroni and all of those that can actually help us identify whether the you can already identify just by those numbers that sales 4 or package design 4 is probably the winner. But then between package design 2 and 1, are they actually different versus that difference happened just by chance? If I ask you that question based off of your current knowledge so far, what could you do? We have already made the overall conclusion that package design impacts sales. We have already made that decision based off of this ANOVA. But to take it another step further and figure out between those package designs, which one is impacting the others the most. So if you run some of those tests, you will see that package design 4 will be completely different from the rest. And so clearly it's the winner. It's the number 1 package design I should always choose. But then between package design 1 and 2, if I have to make a choice, what kind of a test would I do based off of what I have learned so far?
Would you just do a t-test between?
Absolutely. You would just do a t-test. The only difference in that approach would be, and then this is where uh, that aspect is vital. You can do a t-test um, right now um, between these two parts, right? Okay. And when you do the t-test, you are going to test between equal versus unequal. Yes, no? Because you are trying to test that those means are different. So equal versus unequal, meaning when you are looking at the t-test output, you are looking at a two-tailed or a one-tailed output.
Two-tailed.
Two-tailed output. You are looking at the two-tailed output p-value. So when you look at the two-tailed p-value, you would compare that against what? Ideally, so far what we have done is when you look at that p-value, compare that with what?
Alpha.
Alpha, right? Here we make a little bit of a difference. Okay, instead of for when you are taking any two of these package designs and doing a t-test, instead of comparing against alpha, you would compare against what we call a Bonferroni alpha. The Bonferroni alpha is essentially a revised alpha based on the number of levels in the factor. How many levels do I have in the factor? Our factor is package design. How many levels do we have?
4.
4, and therefore the Bonferroni alpha is your alpha over 4, which is equal to 0.05 divided by 4, which is equal to 0.01 and what? 0.0125. So when you compare each one of these pairs, and when you look at their p-values in a t-test, the only difference is in these situations, you will compare that p-value not against an alpha of 0.05, but against an alpha of 0.05 divided by the number of factors. So that is what is called a revised alpha or a Bonferroni alpha. And what can very well happen is statistically you may come up with the idea that there is really no difference between package design 1 and package design 2. And then you can look at the actual logistics of those package designs and come to the conclusion that package design 2 is so much simpler than 1. It will take so much less to create that design in terms of resources, in terms of time, that we can completely take out package design 1, because statistically there is no difference in the sales values that we are getting from these two designs. So that is where these kind of numbers help us in making decisions. Now, in R, if you open up R Commander, okay, this is a hardcore statistics software. So this is much more easier. It requires the data in its crude form. It doesn't require too much more. So you look at the data tab on the top, the data ribbon on the top. You import data from Excel file, okay? And let's suppose we call that P design. Don't keep a gap here, okay? Make sure that all the letters are aligned and there is no gap in between. Hit OK. And it will ask you which data set you are trying to open. So make sure that you open the package design _ ANOVA data set. And when I click on that, of course, it will ask you which of those tabs you want to open, because the R commander works off of each tab. Okay, and I want to only use the for other software tab. Okay, because it is the raw data just the way it is. Okay, so if I basically look at the messages, it says the dataset P design has 13 rows and 2 columns. I can actually view the dataset, and um, it will show up as a different. Hold on a second. Let me share that screen. Can everybody see my screen here? Timothy, can you see my screen? Does it show R commander?
Yes, Dr. B.
Okay, good. So once you have the data ready, now the ideal thing is to do a, and this is something I will continue preaching, always do a visual first to get an understanding of how the data is coming across. And so one way of looking at the visuals is just doing a graph and do a box plot. Okay. And so you are doing a box plot of sales and you plot it by groups. Oops. Oh, I have to make some changes here. Give me a second. So this is my data. I think it is still considering my P design as a column here. So when you look at the data set, R commander also by default understands that the package design 1, 2, 3, 4, because it's numeric data, it's numbers. It's not considering that as a factor yet. And so what you want to do is go under data and you want to go under manage variables in active data set. Okay, so under data, if you go under manage variables in active data set, there is something called recode variables. Okay, so all I'm trying to do is the package design is essentially being recoded as a factor. So now 1, 2, 3, and 4 would be 4 levels of that factor. Okay, so new variable name will be P design. I just changed the name from a lowercase d to an uppercase d to make it sound unique. Okay, and so well, I hope it worked. And so now this time, let me see if it works. There is a bug somewhere here. Let me work with this for a second. I'll come back. Let's let's come back again around. So apparently, I think I was using the wrong drop down. It's a much simpler setup than that. So if you go under data, and under data, if you choose the drop down that says manage variables in active data set, you can, rather than choosing the record variables option, if you drop down, you will see an option that says convert numeric variables to factors, which is essentially what we are after. The p design variable is 1, 2, 3, 4. And so that's how it is essentially looking at it. And all we want to do is choose that p design variable, and um, we convert that into factor levels, where we say use those numbers as those factors. Okay, so here those numbers are 1, 2, 3, and 4, whatever those package design numbers are. And we want to use the new variable name or prefix. We want to keep the same as variables, so nothing change happens. You hit enter, and therefore it asks you, variable p design already exists, override the variable. You say yes, and so now it has used p design as a factor in that variable. So what will now happen is, if I go back to graph and I want to do a box plot, as you can see, only a single variable here is available against which I want to do a box plot by groups. And the group here will be my p design. And so when I plot the sales by p design, I hit OK, it provides me my box plot. And as some of you were looking at the Excel data set, can everybody see the box plot output on my screen?
Yes.
Yes, no?
Yes.
Timothy, can you see? Sarah Aljarani, can you see my box plot output?
Yes.
Okay, so as you could see, the package design 4 clearly represents a very different outcome compared to all the others. Okay, and so it feels that package design 4 is clearly generating much more sales than the others. We just don't know it statistically yet, at least in R. We haven't done the ANOVA test. But this is a smell test, if you will, by visualizing the data. And then there may be a little bit of interference between 1 and 2, and that would be a nice thing to see if they are actually different, or that difference happened by chance. Okay, so to eventually get there, um, what you want to do is, under statistics, under means, you have something called one-way ANOVA. Okay, and so when you do the ANOVA one way, it's going to ask you, by default, it has already set up your groups. Your groups are p-design. Your response is sales. You want to do pairwise comparison of means. Okay. And then do a Welch F test, assuming equal variances. If you do all of those things together, it will give you everything that you need. So it now compares everything, provides you the residual comparison, and so does a lot of output is provided to you. Let's go over some of these in bits and pieces, and then we will look into what they mean in the context of things. Okay, we'll look into multiple comparison of means, and this is called a Tukey contrast. This is the same, very similar to the Bonferroni, where they look into each pairs. So they are comparing um, package design 2 to 1, 3 to 1, 4 to 1, 3 to 2, 4 to 2, 4 to 3, and they're trying to see if there is a real difference between them, or that difference happened just by chance. Okay, and so you will see that between most package designs, okay, and especially package design 4 is clearly different from the rest of the crowd. Okay, so 4 to 1, that p-value is 0.001. 4 to 2, that p-value is less than 0.001. 4 to 3, that p-value is 0.00803. So naturally, as you saw in the box plot, package design 4 is clearly different from the rest. Okay, and so it is the clear winner. Now, um, here is where the interesting part happens. Between package designs 3 and 2, that probability value is 0.01456. Okay, and so that, and between package designs 2 and 1, that probability value is 0.25779. So you can clearly say that statistically there is no difference between package designs 2 and 1, even though in the box plot package design 2 looked to be a little bit higher than package design 1, but statistically there is no difference between those two. And so there's a lot of other tests that also can happen from a fit perspective that look into all of those different aspects. But when you look into the one-way test, this is the outcome that you see. Your p-value or f-value is 27.146. Your p-value is 0.00758, and so overall you are going to see uh, that your package design impacts sales. Okay, so again, as you could see, this is a much more powerful software, and therefore it gives you so much more for the buck as opposed to what Excel does. In Excel, you have to go in and check for each of those post tests, and here all of those post tests can be done for you. And that's the big difference between using a statistical software versus using Excel.